It is a genuine privilege to introduce today's keynote speaker, Dr. Willard F. Libby. Dr. Libby is a native of Grand Valley, Colorado. He earned his BS and PhD degrees at the University of California at Berkeley. Upon graduation from the University of California, Dr. Libby joined the staff of his alma mater. He also served on the faculty at Princeton University, Columbia University, and the University of Chicago before being appointed to the U.S. Atomic Energy Commission by President Eisenhower in 1954. In 1959, Dr. Libby resigned his position with the Atomic Energy Commission to become professor of chemistry at the University of California at Los Angeles. He entered his present position as director of the Institute of Geophysics and Planetary Physics in 1962. As a physical chemist specializing in radiochemistry, Dr. Libby has conducted research in the fields of hot atom chemistry, tracer techniques, and isotopic tracer work. He became well known while at the University of Chicago for his work on natural carbon-14 and its application to dating of ancient archaeological artifacts, and for work in natural tritium and its use in hydrology and geophysics. He is the author of Radiocarbon Dating and more than 275 articles which appear principally in scientific journals. Dr. Libby has received numerous awards. Among these are the John Simon Guggenheim Fellowship, the Research Corporation Award for Radiocarbon Dating Technique, the Chandler Medal by Columbia University for outstanding achievement in the field of chemistry, the American Chemical Society Award for nuclear applications in chemistry, the Willard Gibbs Medal Award by the American Chemical Society, the Day Medal of the Geological Society of America. Recently, Dr. Libby was awarded the California Alumnus of the Year Award. He has received the Albert Einstein Award, and he was honored with one of the world's most esteemed awards when in 1960 he received the Nobel Prize in Chemistry. It is indeed a distinct honor to present Dr. Willard F. Libby, who will speak on the topic, Radiocarbon Dating. Dr. Libby.
Thank you, Professor Zemek. It's an honor to be invited to talk about radiocarbon dating in this science lecture and discussion series. The radiocarbon dating principle, though simple, is strange, so I must take some time to describe it to you. It is that cosmic rays write into our bodies a record of our history. It's very simple to say, very hard to understand. Cosmic rays have an extraordinary ability to transmute matter. I imagine most of you know what transmutation means, but at the risk of boring you, I'll remind you that it means the transformation of one chemical element into another. The ancient alchemists sought to make gold out of lead, and so, in fact, the science of chemistry came out of these efforts of theirs. Well, the cosmic rays do it with great ease, and they transform nitrogen in the air into carbon. The carbon which they make, however, is radioactive carbon, and it is the radioactive carbon that we use for dating. Radioactivity is a characteristic of matter which can best be described as giving it a temporal, finite lifetime. that is, the radiocarbon produced by the cosmic rays, lives on the average 8,300 years. The concept of life for atoms has to be dealt with care. Atoms do not grow old. Nevertheless, they have a lifetime. That is, radioactive atoms. Most of the atoms of which we consist, as far as we can tell, live forever. But radioactive carbon, like many others, have a finite lifetime, and the radioactive carbon atoms live on the average 8,300 years. Now, this characteristic of having no sense of the passage of time, but on the other hand, having a finite time in which to live, is radioactivity. Any atom of carbon that is produced thereafter has the chance of reverting to nitrogen, and you note it does go back to the element from which it was made, of reverting to nitrogen, one chance in 8,300 for each year of its lifetime. Now, being carbon and being made in the air as a result of the cosmic ray bombardment, see, the cosmic rays come from outside the Earth. The radiocarbon burns and becomes carbon dioxide. And again, at the risk of boring you, I will remind you that our substance and source is atmospheric carbon dioxide. If there's any one thing from which we come, it is atmospheric carbon dioxide. We consist essentially of atmospheric carbon dioxide, water vapor, sunlight, and a handful of salt. So the cosmic rays make us radioactive. For in introducing radioactive carbon into the carbon dioxide of the atmosphere, the winds, of course, mix it. The cosmic rays put into living tissue radioactive carbon. Now, 8,300 years is a very long time. The radiocarbon atoms in your body, on the average, were produced before Moses was born, before the dawn of human history, just to give you a faint idea of the span of time they cover. Therefore, in this great length of time, there's ample opportunity for the winds to mix the air. And in fact, the radiocarbon in your body has probably been in the air a half a dozen times. That is, previous hosts have died, their bodies decayed, carbon dioxide gone back into the air and reassimilated, and it's made the round trip many times. I should hasten to add at this point that is the main hold-up, the main destination, the main fate of atmospheric radiocarbon is not to be part of the tissue of living beings, but to become dissolved in the ocean as part of the sea salts. The ocean is so vast and so deep that the carbonate and bicarbonate in the sea salts is more important than all living matter by a factor of 30. So it is that we find that the radiocarbon is mainly controlled by the ocean. And when living conditions vary on Earth, as they have dramatically in times past, particularly during the ice ages, and the amount of living matter undoubtedly is varied by large factors or large percentages, the ocean is a stabilizing influence, so that the amount of radiocarbon in a given amount of carbon is not variable. I'll say that again because it's very important to radiocarbon dating. There are two basic assumptions we find necessary to do radiocarbon dating. One is the cosmic rays have remained constant, so the production rate is constant. And the other is that the oceans have remained constant in volume and in composition. Now, even though radiocarbon has a lifetime of 8,300 years, this is a short time in terms of the geological history of the Earth. As a result, the constancy of the ocean is a very reasonable assumption. So we're left only with the assumption that the cosmic rays have remained constant. For if we do assume that the rate of production is constant, and if we do assume that the dilution is constant, then we can say that all living matter during all time, while alive, has had the same concentration of radiocarbon. That is the same amount per gram or per ounce or per pound. Now, while we live, we continue to mix with the atmosphere through the food we eat. The carbon in our body comes entirely through the food we eat. And the principle of radiocarbon dating is this very, very simple one, namely that when you die, you quit eating. When you die, you quit eating, and therefore, the resupply of the 1 part in 8,300, which disappears each year, is cut off. While you are alive, you eat just exactly the right amount of carbon to compensate for the decay of the material in your body. But when you die, the replacement process is terminated. So it is with all living matter, be it a tree or be it an animal. And the principle is that the disappearance is determined by the law of radioactive decay. Now, those of you who are mathematicians and logicians will be able to understand from what I've said about the nature of radioactive decay that it follows the following mathematical law. The amount that's left is a function only of the time and of the 8,300 years. In fact, we have a parameter which we call a half-life. For radiocarbon, this is 5,730 years. This is the time in which half of any given amount will revert to nitrogen. So after 5,730 years, a body that has been buried should have 1/2 the radiocarbon content per gram of carbon that a living body has. And after twice 5,730 years, that's 11,460, it will have 1/4, that is 1/2 of a half. And so it goes without, in principle, there's always some left. But after 10 half-lives, you will have 1 part in 1024, that being the 10th power of 2. This is such a small fraction that it's very difficult to measure. As a practical matter, radiocarbon dating is limited to about 50,000 years because the measurement of the small residuum is very, very difficult. So what we do in radiocarbon dating is take a part of the living matter and determine the radiocarbon concentration, compare it with that of living matter, the present-day living matter, and then look on our curve to see how many half-lives it is, and from this calculate the age. It's really simple. We use about an ounce of material usually. Actually, we needn't use the entire ounce because the amount that is required to fill our counters is about 1/5 of an ounce. But our care of cleaning the samples requires that there's considerable attrition, and we like to have enough material to make check runs. At the present time, there are some 20,000 radiocarbon dates in the literature. I'll pick a few of these as examples and hope that if you have additional questions and queries, you'll look in the original literature. In the magazine Radiocarbon, published by the Yale University Press, all of these dates are collected in one place. Now I'll go through this story with the slides. We can have first slide, please. This is a cartoon that represents, in a general sort of way, the what I've told you. We have the cosmic rays which produce neutrons. I haven't time this morning to talk about neutrons, but they are the intermediate which actually work on the nitrogen and make it into radiocarbon. They're produced by cosmic rays. And there are 2 carbons made every second on the average over the whole Earth's surface. Though, as the next slide will show, the local production rate is very variable with latitude, because the cosmic rays are charged particles and the Earth is a magnet. The result is a great concentration of cosmic rays near the poles. So the result, the carbon-14 production rate is much higher near the poles. You might, at a first thought, think that would mean that trees and people living in northern and southern latitudes would be more radioactive. Well, that would be so, except for the long lifetime of radiocarbon. It actually isn't so because of the very long lifetime. Nevertheless, taking the Earth as a whole and assuming the cosmic rays have been constant, the carbon-14 will accumulate until its rate of disintegration just balances its rate of formation. So we can say that there must be an amount on Earth which just gives 2 disintegrating carbon-14s per second for each square centimeter. Now, if we go and add up how much carbon there is in the ocean and how much in living matter, we get about 8 grams. And since we have deduced that there must be 2 disintegrations per second in 8 grams, we have already calculated the specific radioactivity of living matter. And this turns out to be about right. This shows a black box, and as you see, it's mainly ocean salts. The biosphere of which we are part is only 1/3 of a gram. The atmospheric CO2 is 1/8 of a gram. The dissolved organic matter in the ocean is more important than the whole biosphere. It's a fortunate thing for radiocarbon, as I said earlier, that the ocean is the main thing. It buffers and makes the concentration stay constant. This is a variation of the neutron concentration, that is the production rate with altitude. And as you see, most of the carbon is made at about 5 miles height in the air. Incidentally, the turning over at the top is very interesting. That's due to neutrons which are produced pointed outward, and they escape the Earth before they make radiocarbon. This is the apparatus in which we burn our materials. That long horizontal tube you see there is we put our samples in it and pass oxygen and mixed with argon over it and heat them with the burner that you see on the little shelf. Then the sample will catch fire, and we save all the gases, and in particular the carbon dioxide, of course, which we place in our counters. This is the purification line. The carbon dioxide must be very carefully purified. This is a picture of the counter. You see it there in the shield with the doors open. The next slide is a better view of it. The radioactive carbon is in such low concentration that it's necessary to shield the counters very carefully from outside radiations in order to get an accurate measure. The counter has a volume of about 8 liters and is filled to about 1 atmosphere of carbon dioxide, pure carbon dioxide. With this counter, a piece of modern wood will give us about 60 counts a minute, whereas a piece of very ancient wood that no longer has carbon in it will give about 15 counts a minute, net difference of about 45. So we have a good appreciable count rate measure on which to work. Now, when we began this research at the University of Chicago, one of our principal problems was to test whether this assumption that the mixing was good over the entire surface was correct. And Dr. Ernest C. Anderson took his PhD with me there on this question. These are the sites from which he took wood samples for measurement. His results are shown here. Took white spruce from the Yukon and from Sweden, wood from Chicago, Switzerland, and all the way to the South Pole, including actually some meat, from seal meat from Antarctica. And you can see that within the area of measurement, the concentration was constant, and quite close, incidentally, to the value we predicted. That's important because of the assumption that we had made that the cosmic rays had remained constant. For you see, our prediction was based on the measure of the present level of cosmic rays. And these data of Dr. Anderson's were the average of the cosmic rays over the last 8,300 years. The agreement between the two gave us reason to believe that our fundamental assumption necessary for radiocarbon dating was correct. Now, on this slide, you see the test to prove whether we do get the right dates. Dr. James Arnold, now of the University of California, San Diego, was my collaborator in this phase of the research. We obtained samples from various museums and measured their radiocarbon content and compared it with the radiocarbon content we would calculate from the historical dates. In other words, we have plotted here the radiocarbon content vertically in units of modern carbon, and horizontally we plotted the historical age. And the line drawn in is the line we would predict, assuming that the radiocarbon dating method was absolutely accurate. Well, beginning in the dawn of history, which is the first dynasty of Egypt, at about 5,000 years ago, and coming to the present time, we have a gratifying agreement with the observations. That isn't to say there aren't deviations. In fact, we know now, with more accurate measures, that there are appreciable deviations of 30 years, 50 years or so, even perhaps 100 years sometimes, due to small fluctuations in the cosmic ray production rate, presumably. See, the cosmic rays come from outside the solar system, and the sun's magnetic field and the Earth's magnetic field deflect them. I told you that the cosmic rays are more intense at the poles due to this deflection. They are also shielded from the Earth itself by the sun's magnetic field and magnetic phenomena. So as the sun varies, there is a chance that the cosmic rays will vary. By studying the radioactivities in meteorites, we have been able to show that the variation is small, because the meteorites are outside the Earth until they hit it, and we pick up a freshly fallen meteorite, we can find the radioactivities in it, and comparing the intensities of the radioactivities of various lifetimes, we can compare the intensity of cosmic rays over these various lifetimes. Though the data are not extremely accurate, it's possible now to say that the cosmic rays back to 100 million years have been constant to something like 40%. Well, that's a large error, but it's better than nothing. And all we know seem to indicate that they are constant, but they may vary by a few percent from time to time. In any case, here is the proof of the pudding, so to speak. We have here a fair sampling of materials collected over the span of human history and find that the radiocarbon dates agree. Some of the samples are interesting in their own right. Beginning with the Egyptians on the lower right, we have, one of the most interesting ones is the one labeled Sesostris at about 3,800 years. If you've been in the Museum of Natural History on 12th Street and Roosevelt Road in Chicago, you may have seen this object. It's a funerary ship that was put in the tomb of Sesostris III, the Egyptian pharaoh, Sesostris III. And we have wood from that ship, which we measured. As a matter of fact, you'll see a hole in the deck where they took the sample. Brings out a point about our difficulties. When you have a large piece of wood, you have tree rings. And we, of course, date for the very year. And if you have a piece of wood that covers several hundred years, you would have a natural built-in error. You can see that in the sample above Sesostris there, labeled redwood. This is the heartwood of a tree whose outer bark was of 0 age. As this tree was cut recently, but had 3,000 rings in it. The horizontal arrow on the point labeled redwood corresponds to 108 rings. Now, as you see, it agrees perfectly that heartwood gives a radiocarbon corresponding to the time that was the outside of the tree. So returning to our funerary ship in Sesostris III, where we had a deck plank, you can see we have a natural error. But we can make some estimates of the number of tree rings and in this way correct for it. The material we prefer is young organic matter, like charcoal. Charcoal normally made by burning of small twigs and small limbs, or cloth, which is made from freshly grown material, or flesh. Your flesh in your body is no older than 18 months. Even your brains are no older than 18 months. We've done this by testing actual human bodies. The only part of your body which is older than 18 months is the protein in your bones. So we like material which is turning over. Trees aren't that way, and we have to be very careful with large blocks of wood that we get too old in age. The sample labeled the Bible is a manuscript of the book of Isaiah of the Dead Sea Scrolls. Sample labeled Pompeii was a biscuit taken from an oven which a lady was baking that fateful morning. Well, each of these samples has an interesting story, and I'm sorry I haven't time to tell it. But they have served our purpose of checking the method. Now, at the present time, we do believe that tendency of the Egyptians, which you see on the lower right, to be a little bit above is really true, and that radiocarbon does indeed need a little bit of correction in the 4,000 to 5,000 year span. Though this curve doesn't show it, there are also corrections of 50 years or so in the time around 1500 AD. We've been working on some English manor houses and find from these that it's necessary. These are some dates I've just picked at random. This is the great Cathedral of Santa Sophia in Istanbul. The date at which it was built is very well known, but then during the Middle Dark Ages, the records were not kept. The architects have been interested in the times at which various new architectural features were built into the cathedral. So we've determined these for them by making measurements. I said we were working on English manor houses. This represents one of them. We find, for example, that the main post dates from the 9th century. And yet the very outermost part is like the 16th century. As you might expect, these great houses are continually under repair and replacement, and it's rather fun to go through them and say what was put there in each century. We've done similar things in French chateaux, and go back to the 4th century in France, checking very well, providing we make these little small corrections that I've been referring to. Perhaps our most interesting general result is that man came to America only 12,000 years ago. This in the face of the fact that man at that time was just like us. He was just as bright as we are and has just looked very much like us. It's very strange that he didn't find his way to the Americas sooner, but as you see here from this plot, there is very little evidence that he was here before the last ice age. The last ice age occurred at about 11,400 years ago. And at this time, the Bering Straits was dry, and it was possible for him to walk across down the west coast, which is now submerged by 150 feet of water, and then inland. That is, he didn't walk across into Alaska. He walked across and down what was then the west coast, and then inland. We find the earliest man in all the 3 American continents the same at around 11,000 years. We found him all over North America at that time, and Central America and South America. Most recent is from the Peruvian Andes. We found him there at that time. Now, these are some of the samples. On the left, you have a piece of 22,000-year-old glacial till wood, which was covered by the Ice Age, the 3rd Ice Age back. glacier covered this forest. On the right, you have the manure, the dung of an extinct animal, the giant ground sloth, which became extinct about 8,000 years ago. From the seeds and so on, you can tell that he was a vegetarian and he ate grass which no longer grows in Nevada. The grass that he was living on normally grows 6 feet high. Obviously, the climate has changed. On the left is a typical piece of basketry. There are tons of this in various museums in the West, which are very ancient. On the right are some plastic replicas of the arrowheads of the earliest American. One is a Folsom arrowhead, the other is a Clovis, and the third is a Lindenmeyer. And these are all contemporaneous. On the left are the linen wrappings of the manuscript of the Dead Sea Scrolls I mentioned. We often do not date the most valuable parts of these materials, but the things which the museum keepers wouldn't want anyhow. On the right is a lock of hair from a body of a woman found in the sands of Egypt 5,000 years ago. I think you'll notice it's dyed. In the center is one of the most remarkable things in human history. This is a 9,000-year-old shoe. This was found in a cave in eastern Oregon, part of a cache of 200 pairs or 300 pairs of these. Found just by chance, this cave was covered by a volcanic eruption very similar to that which covered Pompeii. And just by chance, the archaeologist who had been working with the road crew, in fact had cautioned them to keep their eyes open, ran out of shellac. And he didn't shellac all of them. You see, shellac ruins the material for radiocarbon dating. And so we had some 6 pairs which we could use for radiocarbon dating. That shoe is twice as old as Moses, twice as old as recorded human history. It's the shoe the first American wore. On the right is just a piece of ordinary 2,500-year-old rope. I'd close by pointing out probably the finest thing in human records, the beautiful paintings in the Lascaux Cave in central France. These paintings are somewhat over 15,000 years old. We know that from the charcoal that was found in the floor of the cave. In fact, the archaeologists think, Professor Mobius particular of Harvard thinks the paintings are older than the charcoal. That wonderful work was done by people who lived 15,000 years ago. You notice the animals no longer in Europe. Well, I'll close with the thought that the writing of human history by cosmic rays seems to be one of the main functions of cosmic rays as far as mankind is concerned. It's a kind of unbelievable story, but I hope you believe it's true.